Hello students, it's Dr. D again. I am going to use this time to present to you our exercise that we're going to be doing using the VSEPR theory. You're going to be given a worksheet on your Canvas page. You'll have to download and either work on it in your screen or maybe print it or maybe just do it on a piece of paper. You're going to be essentially be given a series of formulas that you'll have to convert into Lewis structures and then finish out the molecular geometries and the polarities of these molecules. Let me show you what that looks like. This is essentially the practice worksheet that you'll be downloading. It's 2 pages long. And just to show you a little bit of what it looks like, you're going to have a list of compounds with their formulas. You'll have to calculate the total valence electrons. You'll have to calculate what is the Lewis, draw the Lewis structure, including resonance structures. Some of these, you're going to have a comment here that will tell you if you need to draw a resonance structure or not, or any other conditions that apply. You are then going to determine what is the ABE structure. Let's look at a table that I'm going to give you also. This VSEPR table looks like this. Again, let's zoom in so we can see how it works. So essentially what this table does is it's a grid format, kind of like the battleship game. On the left here, what you will do is once you have your Lewis structure, you're going to count what is the steric number. In other words, how many electron groups are attached to the central atom. And we go from 2 to 6. That's as far as we go. Then you'll have to decide on the first column, what is the basic geometry? That is the geometry of the electron groups alone. And you can see them here, the sequence, right? For 2 of them, it's linear. For 3, it's trigonal planar. For 4, tetrahedral. For 5, trigonal bipyramid. For 6, octahedral. Now, it may be that when you draw your Lewis structure, you will find that some of the electron group positions are occupied by lone pairs. So this table allows you to basically kind of skip over to wherever you need to. For example, if you have 3 electron groups, but one of them is a lone pair, you have this structure here. It's still a trigonal planar electron group arrangement, but the shape of the molecule is actually bent. Let's jump down here to, for example, steric number 5. The basic shape here for the electron group is trigonal bipyramid. But if you have one of those positions occupied by a lone pair, and like we said, it's going to be an equatorial position, you're going to have what we call a seesaw shape. If 2 positions are occupied by lone pairs, then it'll be T-shaped. And if all 3 equatorial positions are occupied by lone pairs, it'll be a linear shape. So essentially, these are the scenarios that we have discussed in class. On a separate part of this presentation, I'm going to walk you through some of these shapes so that you can see them in 3 dimensions. All right. So let's go there now. And when we come back, I'm going to walk you through a sample exercise using the worksheet and using this table. Okay, students, I'm going to walk you through a graphic demonstration here of the different shapes according to what we studied in class. What we're going to see is just models of molecules. We're going to focus on the central atom, and we're going to be adding different types of electron groups around it. We're going to start with the simplest structure where the central atom has 2 electron groups around it. And there are several ways you can do that. You can do it this way, which is, for example, like beryllium hydride or beryllium chloride. But we could also do it in the following way. We could also do it by adding, let's say, 2 double bonds. And don't forget that these structures, you can kind of spin them around and see them from different angles. The point is that you have essentially a linear structure, right? The electron geometry for this is linear, and so is the molecule geometry. You can actually do structures, for example, a single and a triple bond, such as the molecule of HCN. Let's put it this way so you can see it. It'll be H center carbon, nitrogen on the right. That'll be an example of this structure. All of these structures, notice that the number of bonds that connect two atoms does not really count. It's more like one electron group on each side. Let's look at what happens when we have 3 electron groups around the molecule. This gives us, as you can see here on the bottom left, a trigonal planar electron geometry and also a trigonal planar molecular shape. Realize that you can replace one of those, for example, with a double bond, such as in the molecule of formaldehyde that we studied in class. And that again, the double bond does not change the fact that there's one electron group connected to this central atom, as well as these other two. It becomes interesting when you start replacing some of these with lone pairs. For example, if instead of that I had a lone pair, notice that now, although the electron geometry continues to be trigonal planar, the shape of the molecule is bent because the lone pair is not visible in the molecular shape. The case where you have the 3 electron groups being atoms, we call that the AB3 setup. When you have one of them replaced by a lone pair, when you have one of them replaced by a lone pair, we call that structure the AB2E structure. Let's see what happens when we have 4 electron groups around the central atom. This is the famous tetrahedral shape, and remember that we can draw this in different ways, and we typically put one of the atoms on the top from our perspective. But remember, molecules are not static in space, they spin around. And this would be called the AB4 arrangement, which gives us a tetrahedral electron geometry and a tetrahedral molecular geometry. You can see the on the bottom left here what we're ending up with. Don't forget, the angles here are 109.5 degrees. Now, what happens if we replace one of those positions with a lone pair? And I'm going to move the lone pair to the top to give us a sense that we're looking at the new molecular geometry, which is a trigonal pyramidal. Now, typically, the angles here, you would predict that they're also 109.5 degrees, but many times what happens is those angles get somewhat compressed because of the extra repulsion that is produced by this lone pair over here, as we discussed in class. We could also change that structure into something that now has 2 lone pairs. Again, the electron geometry continues to be tetrahedral, but the actual shape of the molecule is what we call bent. Now, we said that for molecules made with a central atom off of the 3rd or 4th period, we can actually have the central atom expand beyond the octet. And so what you can have is you can have actually 5 electron groups on that central atom. And the important thing to remember when we look at this structure is that there are 2 different kinds of positions in this shape, which is called trigonal bipyramidal. We have 3 groups that are lying on the same plane at 120-degree angles from each other, right? And I don't see them here, I'm sorry. Forming actually a triangle here around the central atom. And then at 90-degree angles, you have these 2 positions here, one above and one below the plane of that triangle, which are called the axial positions. When we replace one of these guys with a lone pair, it turns out that the position that gets replaced is one of the equatorial positions. And what you end up with is a structure that's commonly called a seesaw shape. If we replace another one of these with a lone pair, again, the equatorial positions are the ones that are going to be occupied, and you end up with something that is sometimes called a T-shape, although it's somewhat distorted. The electron geometry continues to be trigonal bipyramidal. And finally, we can have a situation where another one of the atoms is replaced with a lone pair, and then you have what we call a linear geometry, because the three lone pairs have been placed in the formerly equatorial positions of the trigonal bipyramidal structure of the electron groups. Let's see what happens when we add 6 total bonding groups. There we go. I'm going to take the bond angles out of here. And again, what you can see here is the electron arrangement is what is called an octahedral arrangement. And if all 4 of the electron groups are atoms bonded, the molecule will also be octahedral. If we replace one of those atoms with a lone pair, all of the positions are equal. And so what you end up getting is what is called a square pyramidal shape. You can see I'm going to put the lone pair on the bottom. You can see the base of this square pyramidal geometry for the molecule. If we want to replace another lone pair at this point, what we want to minimize is the repulsions. And so the atom that was formerly diametrically opposed to where the lone pair was, that is the one that is going to end up being replaced. And as you can see, we're going to end up with a structure that's commonly called a square planar geometry. So this is a brief catalog of all the different shapes so you can see them in three-dimensional space. Don't forget that these things, again, like I said, you can rotate them around. And so there's nothing to restrict where those lone pairs are. What is important is to maintain the perspective and the connections between the atoms and the central atom. Okay, students, now that we have a good view of the three-dimensional shapes of all these molecules and how the different numbers of electron groups and the distribution between atoms and lone pairs on the central atom determine the molecular geometry, let's do a practice exercise. You're going to be asked to download this form from Canvas, and this is going to be your worksheet. You can choose to print it or do it by hand, or if you can fill it in on the screen, if you have the software, you can do that. But essentially, there's several things you're going to be doing here. You're going to be given a set of compounds with their formulas, and you're going to be asked to carry out several tasks in here. So for example, let's take ammonia as our practice here, right here. We know that ammonia has 8 valence electrons, and we've already done the structure for it. So this would be the Lewis structure for ammonia. Don't forget that how we place these atoms in our picture really doesn't matter that much as long as they're connected in the proper way. We have what is called the ABE or AXE designation over on this column here. The idea is how many of the electron groups are bonding atoms, how many of the electron groups are lone pairs. In this case, we have 3 bonding atoms, and we have 1 lone pair, so it will be AB3E. Sometimes in some contexts, some authors prefer to say AXE instead of ABE. That's perfectly fine. It's essentially the same thing, all right? Now, the next one is we're going to determine, well, what is the hybridization on the central atom of the ammonia molecule? If you remember, the way that works is hybridization is the proposal that atoms are able to form these different bonding structures by combining atomic orbitals and making hybrid orbitals that have new geometries. So in the case of, let's say, ammonia, what we had to consider is what is the steric number? So in our format A, B, M, E, N, the steric number is the total number of electron groups. In other words, M plus N. In the case of ammonia, since we said that our structure was this, we would say that the steric number is 1, 2, 3, 4. That is how many, this number tells me the number of hybrid orbitals required. So that means that in order to make this compound, nitrogen is going to have to take an s orbital and 1, 2, all 3 of the p orbitals to get 1, 2, 3, 4. And so we would say that the type of orbital that is made here by hybridizing these 4 is an sp3. Notice the superscripts 1, which is implicit, plus 3 equals the 4 orbitals that were used to build these 4 hybrid orbitals. And so coming back here to our worksheet, we're going to find that this is going to be on the next column, hybridization of the central atom is going to be sp3. Now let's tackle the electron group and the molecular geometries. For that, I have given you this chart here. All right, let's take a look at this chart. And this chart is built in the form of a grid. So what you do is you find here on the left side the number of electron groups, the steric number, which we said for ammonia is 4. And now each column represents a number of those electron groups that are lone pairs. In the basic geometry where there's no lone pairs, we can find that the electron group geometry is tetrahedral. So we go back to our worksheet here, and it asks us what is the electron group geometry, and we're going to say that it is tetrahedral. However, when we look at the actual distribution, we see that one of those positions is actually occupied by a lone pair on the nitrogen. And so that means that the shape of the molecule, not the electron group arrangement, but of the molecule is trigonal pyramid. So we're going to come back over here and we're going to say this is trigonal pyramid. If you have small handwriting, you can probably fit in trigonal pyramidal, but I don't. So I'm going to leave it as a trigonal pyramid here. Okay, the next question becomes very interesting. We're going to ask, is the molecule polar or non-polar? Now, to do that, technically, what you have to ask is, are there any net dipoles in the molecule? In other words, are any of the covalent bonds in this molecule not only polar, but do the vectors of those dipoles add up to produce a net dipole for the whole molecule? Well, unfortunately, unless you have a ball and stick models or any kind of molecular models that are three-dimensional, it would be hard for you that mathematically. So what I'm going to do is I'm going to give you a shortcut. Okay, I'm going to give you a shortcut. Let's come over here and let's do a shortcut here. All right, and let's do a what are we going to call this? A shortcut polarity. It's going to be a shortcut. I'm going to say, I'm not going to make too many claims here. So I'm going to say that it's about 90% of the time is correct. All right. So it's effective, let's say 90% of the time. I'm not going to claim that it's any better than that. All right. Okay. So the way I do it is the following. I ask myself question number 1. Are there any polar bonds in the molecule? All right. If the answer is no, then my friends, that molecule is not polar, because you cannot have a polar molecule if there are no polar bonds to deal with. All right. Now, what if there are polar covalent bonds? Is that enough? No, we have to ask another question. The question is, right, we had to add them up. They should add up to a net dipole. But remember, we don't have three-dimensional structures to work with. So what I'm going to ask is, are they distributed symmetrically or non-symmetrically? Dr. DA, that's about as complicated. That doesn't make sense anyway. That's why I said I got to give you a shortcut, all right? The way we're going to do this is I'm going to ask myself, first of all, are there lone pairs on the central atom? If the answer is yes, I'm going to say, you know what? This molecule is non-symmetric. If the answer is no, I'm going to ask another question. I'm going to ask, is everything connected to the central atom the same? It's kind of like a very kind of vague, but I want to keep it that way. Is everything that is connected to the central atom the same kind of stuff? Like I said, it's a shortcut, guys. In other words, let's say there's no lone pairs on the central atom. Let's say there are 3 atoms then. Are they all the same? Are they all fluorines? Are they all oxygens? You know what I'm saying? That's the whole idea here. Let's say there are 5 atoms in there. Are all 5 the same? Or is there one that is different? Well, if the answer is yes, same kind, then that means this molecule is symmetric. In other words, essentially, even if there are any if there are any polar covalent bonds, you know, everything is the same. This molecule is symmetric, and therefore the molecule is not polar. All right. Oh, sorry, I kind of lost my place over here. All right, it's non-polar. Now, if the answer is no, in other words, there are more than one kind of thing connected to the central atom. Let's say there are 4 atoms, but let's say 3 of them are bromines and 1 of them is a nitrogen, or for example, something like that, you know what? Then that means that the molecule is non-symmetric. And if it is not symmetric, then the molecule is polar. Kind of like a little sketchy here. Let me just zoom back out so we can see the whole sheet here at the same time. So again, I'm going to start out with, are there any polar covalent bonds? If the answer is no, molecule is not polar. The answer is yes, that is not enough. I had to ask myself, are they distributed symmetrically or non-symmetrically? But since I don't have a three-dimensional thing and my brain might not have the capacity to visualize three-dimensional shapes on a piece of paper, you know, a flat piece of paper, I'm going to take a shortcut. I'm going to ask, well, are there lone pairs on the central atom? If the answer is yes, I'm going to say, no, they're not symmetric. If the answer is no, I'm going to ask another question. I'm going to say, is everything that's connected to the central atom the same kind of stuff? Are they all the same kinds of atoms? If the answer is yes, and there's no lone pairs, that means the molecule is symmetric, and therefore I'm going to make a shortcut guess that it is nonpolar. If the answer is no, then that means that even with no lone pairs, I have a non-symmetry in that molecule. And that means that if there were any polar covalent bonds in here, they are going to be distributed non-symmetrically. And so the molecule is going to be polar. So let's go back to our friend ammonia. Are there any polar bonds in here? Well, actually, each one of these nitrogen-hydrogen bonds is actually polar because the nitrogen is more electron negative than the hydrogen. So there are dipoles pointing towards the nitrogen from all 3 hydrogens in here. So are there polar bonds? The answer is yes. Now I'm going to ask, is it symmetric or non-symmetric? Lone pairs? Yeah, here they are. There is a lone pair in there, right? So that means that when I draw the actual three-dimensional structure, this is going to be a non-symmetric. It's going to be not symmetric. And therefore, ammonia should be polar. Like I said, guys, 90% of the time this works. Every now and then you have some fails, but that is where having the actual, having the actual three-dimensional structures or models helps you a lot. So I'm going to come back here to the worksheet. And in that final column that I have in here, I'm going to write down that according to my shortcut guesstimate, ammonia is a polar molecule. Okay, you have several other compounds here to deal with. And of course, there's the other side of this. Sometimes you're going to have to be careful because you may have to propose structures that have resonance in them. Also, sometimes when you build the Lewis structure, you might find yourself having to decide between more than one candidate. And so you may have to apply the formal charge criterion. So give yourself time to do this. I am going to post the final solutions to all of these, so you shouldn't have to worry about it. They will be available in your Canvas page before you turn in this lab report, quote unquote. Don't forget, this worksheet is worth 10 points, and combined with the Lewis structures worksheet, which is worth also 10 points, combined, they give you a full lab report score of 20 points. Okay, so I hope you enjoyed. If you have any questions, again, remember, just email me or text me or put a message in Canvas for me. All right, have a good time, and we'll see you soon.